Tonight, we're exploring something that sounds impossible, but happens constantly all around you. Time itself runs at different speeds, depending on where you are and how fast you're moving. Not just appears different, actually runs differently. Your head ages faster than your feet. Satellites orbiting Earth tick forward through time more quickly than clocks on the ground. Particles streaming through the atmosphere live impossibly long lives because time moves in slow motion for them. Before we start, if this kind of exploration interests you, a like or subscribe helps the channel grow. Now let's see how scientists discovered that time is far stranger than anyone imagined. For thousands of years, humans assumed time flowed like a river, steady, constant, universal. A second in Rome equaled a second in Beijing equaled a second anywhere in the universe. Isaac Newton formalized this in the 1600s, describing time as absolute, ticking forward at the same rate, regardless of motion or location. This matched everyday experience perfectly. Your watch doesn't run faster when you drive to work. You don't age differently on an airplane than in your living room. Then, in 1905, a 26-year-old patent clerk named Albert Einstein published a paper that changed everything. He showed mathematically that time must slow down for objects in motion. Not appear to slow down, actually slow down. Every process, every heartbeat, every chemical reaction runs at a different rate, depending on velocity. The effect is tiny at everyday speeds, but grows larger as you approach the speed of light. Einstein's claim seemed absurd. How could time itself change? But the mathematics were solid, following logically from two simple assumptions. First, the laws of physics work the same in all reference frames, moving at constant velocity. Second, light always travels at the same speed, regardless of how fast the source or observer is moving. These two statements, both supported by experiments, led inevitably to the conclusion that time must be flexible. The scientific community didn't immediately accept this. Extraordinary claims need extraordinary evidence. So, over the next century, physicists designed dozens of experiments to test whether time dilation actually happens. Every single test confirmed Einstein's predictions. We're going to walk through the most important of these experiments tonight, building from the simplest to the most extreme. In October 1971, physicists Joseph Hafele and Richard Keating did something that sounds almost comically simple. They bought tickets on commercial airline flights and carried atomic clocks with them around the world. When they returned and compared their clocks to ones that stayed on the ground, the traveling clocks had ticked fewer times. Time had genuinely passed more slowly for the clocks that flew. The experiment used cesium atomic clocks, which measure time by counting oscillations of cesium atoms. These atoms vibrate at exactly 9,192,631,770 times per second when they transition between two energy states. You can count these oscillations and use them as a clock that's accurate to within billionths of a second. Hafele and Keating synchronized 4 portable atomic clocks with reference clocks at the U.S. Naval Observatory in Washington, D.C. They flew 2 clocks eastward around the world on commercial flights. They flew 2 more clocks westward. After completing the circuits, they brought the clocks back and compared them. Einstein's theory predicted specific outcomes. The eastward clocks should lose time because they're moving faster relative to Earth's center. When you fly east, you're moving in the same direction Earth rotates, so you're moving faster through space overall. The westward clock should gain time because they're moving against Earth's rotation, making them slower overall. But there's a second effect. The planes fly at high altitude where Earth's gravity is slightly weaker. Weaker gravity makes time run faster. The researchers had to calculate both effects. The eastward clocks, predicted to lose about 40 nanoseconds, actually lost 59 nanoseconds. The westward clocks, predicted to gain about 275 nanoseconds, actually gained 273 nanoseconds. The small differences came from experimental uncertainties, like variations in the flight paths and altitudes. Within measurement error, the results matched Einstein's equations perfectly. Think about what this means. The pilots and passengers on those flights aged differently than people on the ground, only by a few hundred billionths of a second, far too small to notice, but different nonetheless. Time genuinely passed at different rates. The Hafele-Keating experiment proved time dilation happens, but you might think it's just a curiosity with no practical importance. Then GPS came along and proved that modern technology completely depends on accounting for these effects. GPS works by using satellites to triangulate your position. Each satellite carries atomic clocks and constantly broadcasts its location and the current time. Your GPS receiver picks up signals from multiple satellites. Since radio waves travel at the speed of light, the delay between when a satellite sends a signal and when you receive it tells you the distance to that satellite. With distances to 4 satellites, you can calculate your exact position. This requires incredible timing precision. Light travels about 1,000 feet in 1 microsecond. If your timing is off by even 1 microsecond, your calculated position could be wrong by 1,000 feet. GPS aims for accuracy within a few yards, which means the satellite clocks and your receiver need to be synchronized to within billionths of a second. But GPS satellites orbit at 12,550 miles altitude, moving at 8,700 miles per hour. At this speed and altitude, 2 separate relativistic effects alter how fast time passes for the satellites. Special relativity says, moving clocks run slow. The satellites are moving at 8,700 miles per hour, which causes their clocks to lose about 7 microseconds per day compared to ground clocks. General relativity says clocks in weaker gravitational fields run fast. At 12,550 miles altitude, gravity is weaker than on Earth's surface, making the satellite clocks gain about 45 microseconds per day. The net effect is that satellite clocks run fast by 38 microseconds per day. Light travels 7 miles in 38 microseconds. Without corrections, GPS positions would drift by 7 miles per day. After 1 week, your GPS could think you're in a different city. The system would be worthless. Engineers solved this by programming the satellite clocks to tick at a slightly different rate before launch. The clocks are set to run slow by exactly the amount needed so that once in orbit, experiencing the combination of velocity and gravitational effects, they stay synchronized with ground clocks. Every GPS satellite in orbit right now has this correction built in. Every time you navigate using GPS, you're relying on Einstein's equations being accurate. Cosmic rays are high-energy particles, mostly protons, that slam into Earth's upper atmosphere from outer space. When a cosmic ray hits an air molecule about 9 to 12 miles up, the collision creates a shower of new particles. Among these are muons, which are like heavy electrons. Muons are unstable. A muon at rest decays into other particles with a half-life of 2.2 microseconds. That means if you start with 1,000 muons sitting still, after 2.2 microseconds, about 500 will have decayed. After another 2.2 microseconds, About 250 remain. The decay is exponential and happens quickly. Even if a muon traveled at the speed of light, in 2.2 microseconds it could only travel about 2,000 feet. The muons created by cosmic rays form about 9 to 12 miles up. That's 47,000 to 63,000 feet. They should decay long before reaching the ground. Almost none should make it. Yet we detect muons at ground level constantly. About 1 muon passes through your hand every second as you sit here. How is this possible? The muons created in the upper atmosphere are moving at about 98% of the speed of light. At this speed, time dilation is significant. From our reference frame on the ground, the muon's internal clock runs about 5 times slower than ours. The muon's 2.2 microsecond half-life becomes about 11 microseconds from our perspective. That's enough time for the muons to travel from the upper atmosphere to the ground before most of them decay. From the muon's own reference frame, time passes normally. The muon still only lives 2.2 microseconds by its own clock. But because it's moving so fast, the distance from the upper atmosphere to the ground appears contracted. What we measure as 9 miles appears to the muon as less than 2 miles. So it can traverse the distance in its short lifetime. Both explanations describe the same physical reality from different perspectives. Ground observers see time dilation extending the muon's life. The muon experiences length contraction, making the journey shorter. Either way, muons reach the ground when classical physics says they shouldn't. You can measure this directly. Scientists have placed muon detectors at different altitudes and counted how many muons survive at each height. The numbers match Einstein's predictions precisely. The muon example happens naturally in the atmosphere. Particle accelerators let scientists create similar conditions in controlled laboratory environments. At facilities like CERN in Switzerland, physicists accelerate particles to speeds within a tiny fraction of light speed, producing extreme time dilation in machines you can walk up to and touch. The Large Hadron Collider accelerates protons to 99.99991% of light speed. That's 7 nines after the decimal. At this velocity, the Lorentz factor equals about 7,000. The Lorentz factor is the number that tells you how much time slows down. A Lorentz factor of 7,000 means time passes 7,000 times slower for the protons than for us. Many particles created in high-energy collisions decay quickly. Pions, for example, have a rest lifetime of about 26 nanoseconds. Even at light speed, a pion could only travel about 25 feet in 26 nanoseconds. But when pions are accelerated to near light speed in an accelerator, they can travel hundreds of feet or even miles before decaying. Their lifetimes are extended by exactly the Lorentz factor corresponding to their velocity. Scientists measure this routinely. They know how long particles should live at rest. They measure how long particles live when moving at high speed. The ratio always equals the Lorentz factor calculated from the particle's velocity. Thousands of measurements over decades at dozens of different accelerators all confirm the same mathematical relationship. Storage rings provide another demonstration. These are circular accelerators, where particles orbit repeatedly. Muons can be injected into a storage ring and allowed to circulate. The muon G-2 experiment at Fermilab uses a 14-meter diameter ring. Muons orbit at 99.9, 4% of light speed, where time dilation extends their lifetime by a factor of about 9. Without time dilation, the muons would decay too quickly to complete many orbits. With time dilation, They survive long enough to go around thousands of times, allowing scientists to make precise measurements of how muons behave in magnetic fields. The experiment only works because time dilation exists. Everything so far has involved velocity time dilation from special relativity. But Einstein's general theory of relativity, published in 1915, predicted another kind of time dilation. Gravity itself makes time run slower. The stronger the gravitational field, the slower time passes. In 1959, Robert Pound and Glenn Rebka tested this prediction using a 74-foot tall tower at Harvard. They put a gamma-ray source at the bottom and a detector at the top. Gamma rays are high-energy light. As a gamma ray climbs up the tower, it's moving away from Earth, working against gravity. This costs energy. The gamma ray loses a tiny bit of energy, which means its frequency decreases. General relativity predicted exactly how much the frequency should decrease based on the tower's height and Earth's gravitational field. The predicted shift was about 2.5 parts in 10 to the 15th power. That's a change of 0.00000000000000000000025. Absurdly tiny. But Pound and Rebka built equipment sensitive enough to measure it. The gamma ray's frequency decreased by exactly the predicted amount. Over just 74 feet of height, gravity's effect on time is measurable. Higher up in the tower, time runs faster by a minuscule but detectable amount. Jump to 1976. NASA launched Gravity Probe A, a rocket carrying an atomic clock straight up to an altitude of 6,000 miles. At this height, Earth's gravity is noticeably weaker than at the surface. The clock ticked faster by the amount general relativity predicted, accurate to within about 1/100th of 1%. Modern optical atomic clocks are so precise they can detect gravitational time dilation over a height difference of 1 foot. In 2010, researchers at NIST built clocks accurate to within 1 second in 3.7 billion years. Raise one of these clocks by 12 inches, and it ticks measurably faster because gravity is slightly weaker 1 foot higher. This opens applications beyond testing physics. You could use ultra-precise clocks as gravitational sensors to map tiny variations in Earth's gravitational field. This might help locate underground water reserves or mineral deposits. Geologists are already exploring this possibility. Gravitational time dilation becomes extreme near black holes. A black hole is a region where gravity is so intense that nothing can escape, not even light. The boundary is called the event horizon. Right at the event horizon, from the perspective of a distant observer, time stops completely. Imagine watching someone fall toward a black hole. As they approach the event horizon, you see them moving slower and slower. Time is passing more and more slowly for them from your viewpoint. At the horizon, they appear to freeze. You never actually see them cross. They're stuck at the edge from your perspective, time having ground to a halt. From the falling person's perspective, nothing strange happens. They don't slow down or feel time stopping. They fall through the event horizon smoothly and continue toward the center. Time passes normally for them. The difference is entirely about reference frames. Both perspectives are valid descriptions of the same event. Light emitted by someone falling into a black hole gets severely redshifted as it climbs out of the intense gravitational field. The light loses energy. Its frequency drops. It becomes redder and dimmer. Eventually, the light is so redshifted it's no longer visible. The person fades from view, not because they're getting farther away, but because their light has lost almost all its energy fighting gravity. Supermassive black holes at galactic centers can have masses billions of times the Sun. Near one of these giants, time dilation is severe. You could orbit just outside the event horizon, experience a few hours, then escape back to safety, having skipped decades into the future for people far from the black hole. This scenario appeared in the movie Interstellar. The characters visit a planet near a massive black hole, spend a few hours there, and return to find 23 years have passed for their colleague who waited at a safe distance. The physics is accurate. We can observe time dilation effects around real black holes. Many black holes are surrounded by accretion disks of gas spiraling inward. The gas experiences both velocity time dilation from its orbital motion and gravitational time dilation from the black hole's gravity. X-ray telescopes can detect light from this hot gas. By analyzing the spectrum, astronomers measure the gas's motion and the time dilation it's experiencing. Observations match general relativity's predictions. Black holes represent the extreme, but neutron stars also produce strong gravitational time dilation. A neutron star packs about 1.4 times the Sun's mass into a sphere 12 miles across. That's about the size of a city containing more mass than the Sun. The surface gravity is about 200 billion times Earth's gravity. Time at a neutron star's surface runs noticeably slower than far from the star. If you somehow survived on the surface for 1 year, only about 300 days would pass from the perspective of a distant observer. You'd age about 2 months less than a year. The difference is substantial. White dwarfs are less extreme, but still significant. A white dwarf contains about half the Sun's mass compressed to roughly Earth's size. This creates strong surface gravity and measurable time dilation. Clocks on a white dwarf's surface tick about 1 part in 10,000 slower than clocks far away. Astronomers can observe this. White dwarfs emit light, and the wavelength of that light is slightly shifted toward the red compared to what we'd expect. This gravitational redshift matches the predictions of general relativity. Every white dwarf we observe shows the expected redshift based on its mass and radius. The classic thought experiment goes like this. You have identical twins, one stays on Earth. The other boards a spacecraft, travels to a nearby star at close to light speed, then returns. When the traveling twin gets back, they've aged less than the Earth twin. They're literally younger. Let's use actual numbers. Say the star is 10 light years away. The spacecraft travels at 99.5% of light speed. From Earth's perspective, the journey takes about 10.05 years each way, 20.1 years total. The Earth twin ages 20.1 years. But at 99.5% of light speed, the Lorentz factor is about 10. Time passes 10 times slower for the traveling twin. They experience about 1 year traveling to the star and 1 year back. When they return, they're only 2 years older, while their sibling is 20 years older. If they were both 30 when one left, the traveler is now 32 and the Earth twin is 50. This seems paradoxical because motion is relative, right? From the traveler's perspective, isn't Earth moving away at 99.5% of light speed? Shouldn't the Earth twin's clock run slow? The resolution is that the situation isn't symmetric. The traveling twin has to accelerate to reach traveling speed, decelerate at the star, turn around, accelerate back toward Earth, and decelerate on arrival. These accelerations break the symmetry. The traveler changes reference frames. The Earth twin doesn't. Acceleration makes the difference. The twin who accelerates ages less. This has been tested, not with humans traveling to stars, but with particles in accelerators that undergo acceleration. Particles that accelerate live longer than particles that don't, exactly as the resolution of the twin paradox predicts. The GPS system actually demonstrates the twin paradox on a small scale continuously. The satellites are in orbit, constantly accelerating as they curve around Earth. Ground clocks are not accelerating in the same way. This creates an asymmetry similar to the twin paradox. If you could somehow run a satellite in orbit for your entire lifetime, return it to Earth, and compare its clock to one that stayed on the ground, the satellite clock would be ahead. It would have experienced more time because the gravitational time dilation at altitude more than compensates for the velocity time dilation from orbital motion. The satellite ages faster in this scenario. For GPS, the net effect is 38 microseconds per day with the satellites gaining time. This has been measured continuously since GPS became operational. The satellites really do tick faster than ground clocks by exactly the predicted amount. This asymmetric aging happens constantly, day after day, with dozens of satellites all showing the same effect. The Lorentz factor determines how much time dilates at different speeds. The formula is gamma equals 1 divided by the square root of 1 minus v squared over c squared. Here, v is velocity and c is the speed of light. At everyday speeds, the Lorentz factor is essentially 1. Walking at 3 miles per hour gives a Lorentz factor of 1.000000000001. You'd need hundreds of decimal places to see any difference from 1. This is why you don't notice time dilation in daily life. At 10% of light speed, 18,600 miles per second, the Lorentz factor is 1.005. Time runs about 0.5% slower, measurable with atomic clocks, but not noticeable in human experience. At 90% of light speed, the Lorentz factor jumps to 2.294. Time passes less than half as fast. At 99%, it's 7.089. Time is more than 7 times slower. At 99.9%, 22.366, over 20 times slower. At 99.99%, 70.712, 70 times slower. At 99.9999%, 707. Time is passing more than 700 times slower. As you approach light speed, the Lorentz factor grows without limit. At exactly light speed, it would be infinite, which is why nothing with mass can reach that speed. It would require infinite energy. Every measurement of particle lifetimes at different speeds confirms this mathematical relationship. The observed lifetime extension always equals the Lorentz factor for that velocity. The equation works across every speed regime that's been tested. Imagine a spacecraft that maintains constant acceleration of 1g, the same acceleration you feel standing on Earth. This would feel comfortable for the crew. They'd experience normal gravity throughout the journey. Accelerating at 1g, the spacecraft reaches 90% of light speed in about 8 months from Earth's perspective. After 1 year of acceleration, it's traveling at 94% of light speed. Continue accelerating, and you get arbitrarily close to light speed, with time dilation becoming more and more extreme. Consider a journey to Vega, 25 light-years away. Accelerate at 1g for half the journey, decelerate at 1g for the second half. From Earth's perspective, this takes about 26.5 years. But the crew experiences only about 6.6 years due to time dilation. They arrive having aged less than 7 years, while over 26 years passed on Earth. For truly distant destinations, the effect is dramatic. The galactic center is 26,000 light-years away. A constant One G journey there and back takes 52,000 years from Earth's perspective. The crew experiences only about 40 years. They could travel to the galactic center and return in one lifetime, while 50,000 years passed on Earth. Everyone they knew would be long dead. Civilization would have completely transformed. These numbers come straight from the mathematics of relativity. We don't have spacecraft capable of such journeys, but the physics is clear. If we ever develop the technology, this is what would happen. Accelerating to relativistic speeds requires enormous energy. The faster you go, the more energy you need, and the relationship is not linear. Energy requirements explode as you approach light speed. To accelerate 1 ton to 90% of light speed requires about 9 times 10 to the 18th joules. That's 9 million trillion joules. For comparison, the entire world uses about 6 times 10 to the 20 joules per year. Accelerating 1 ton to 90% of light speed would consume about 1% of the world's annual energy production. To reach 99% requires much more. To reach 99.9% requires vastly more still. The energy requirements increase exponentially. This might be why we haven't detected alien civilizations visiting us. Even if they exist, the energy cost of interstellar travel at speeds where time dilation helps could be prohibitive. At the Large Hadron Collider, protons are accelerated to 6.5 trillion electron volts per beam. The proton's rest mass energy is only 0.938 billion electron volts. Almost all the LHC's energy input goes into kinetic energy. You're paying an energy price to achieve the time dilation that lets those protons exist long enough to collide and create interesting particles. Cesium atomic clocks work by counting oscillations of cesium atoms. Cesium-133 atoms transition between 2 hyperfine energy states at exactly 9,192,631,770 times per second. This frequency is determined by fundamental physics, the same for every cesium atom in the universe. A cesium clock uses microwave radiation to drive these transitions. When the microwave frequency exactly matches the transition frequency, the atoms absorb the microwaves and change states. You can detect this and use feedback to lock your microwave generator to the atomic transition. Count the oscillations, and you're counting time defined by atomic physics rather than mechanical motions. Modern cesium clocks are accurate to about 1 second in 100 million years. They're the basis for international timekeeping. Since 1967, 1 second is officially defined as exactly 9,192,631,770 cycles of the cesium transition. Optical atomic clocks use higher frequency transitions at optical wavelengths instead of microwaves. Higher frequencies mean finer divisions of time. The best optical clocks using strontium or ytterbium are accurate to within 1 second in 15 billion years, longer than the age of the universe. These clocks can detect the gravitational time dilation from raising them 1 foot. Rotating black holes drag space-time around with them. This is called frame dragging. Close enough to a rotating black hole, you can't avoid being dragged around even if you fire your rockets at maximum thrust. The region where this happens is the ergosphere, located outside the event horizon. In the ergosphere, time dilation is severe, but you can still escape. The combination of rotation and gravity creates complex time dilation effects that depend on your position and your orbital direction. Orbiting in the same direction as the black hole's rotation is different from orbiting against it. The Penrose process, described by Roger Penrose in 1969, theoretically lets you extract energy from a rotating black hole using the ergosphere. You drop an object in. It splits. One piece falls into the hole. The other escapes with more energy than the original object. The extra energy comes from the black hole's rotation, which slows down slightly. Some astrophysicists think this process might power relativistic jets from black holes. Gas falling into the ergosphere could be split and accelerated, launching powerful beams of particles at near light speed. These jets extend for millions of light years in some cases. The expansion of the universe creates another form of time dilation. When we observe distant supernovae, we see the explosions stretched out in time. A supernova that brightens and fades over 30 days in its own reference frame appears to brighten and fade over 60 or 90 days from our perspective, depending on distance. This isn't velocity or gravitational time dilation. It's caused by the expansion of space itself. Photons from the supernova are stretched as they travel through expanding space. This stretches out the time scale of events we observe. Distant quasars also show this effect. Their brightness variations appear to happen more slowly than nearby quasars. Astronomers use this cosmological time dilation to study the universe's expansion history. The amount of time stretching tells you about the expansion rate when the light was emitted. Combined with distance measurements, this reveals how expansion has changed over cosmic time. These observations led to the discovery of dark energy accelerating the expansion. Proton therapy for cancer uses beams of protons accelerated to about 60% of light speed. Heavy ion therapy uses heavier nuclei at about 80% of light speed. At these velocities, time dilation is measurable with Lorentz factors between 1.3 and 1.7. Some particles in the beam decay. Time dilation extends their lifetimes, letting them reach the tumor before decaying. Treatment planning software accounts for relativistic effects. The beam doesn't behave like a classical projectile. Energy and momentum relationships are affected by relativity. Ignoring these effects would cause the beam to deposit energy in the wrong location. Modern medical physics incorporates relativity routinely. This is practical technology where relativistic effects matter for treating patients successfully. If you sent bacteria on a spacecraft traveling at 99.9% of light speed, from Earth's perspective, the journey to a star 10 light years away takes about 10 years. The bacteria experience about half a year due to time dilation. The bacteria age 6 months, while 10 years pass on Earth. This could be relevant for panspermia theories or future attempts to seed other planets with life. Organisms could potentially survive journeys that take decades from Earth's perspective by experiencing only months or weeks in their own reference frame. Time dilation affects all biological processes. Chemical reactions, DNA replication, protein folding, metabolism, everything runs slower from an external observer's viewpoint. The bacteria themselves wouldn't notice. Time passes normally in their reference frame, but external observers see all their life processes happening in slow motion. Storage rings hold charged particles in circular orbits using magnetic fields. The muon G-2 experiment at Fermilab injects muons into a 14-meter diameter ring at 99.94% of light speed. The Lorentz factor is about 9, extending the muon lifetime ninefold. Without time dilation, muons would decay before completing many orbits. With time dilation, they circle thousands of times, letting scientists measure how muons wobble in magnetic fields with high precision. The experiment tests quantum field theory predictions. Any discrepancy could point to new physics beyond the standard model. Electron storage rings produce synchrotron radiation used in materials, science, chemistry, and biology research. Electrons orbit at extremely close to light speed with Lorentz factors in the thousands. Their extended lifetimes let them orbit for hours, continuously producing useful radiation. These facilities exist worldwide and operate routinely, demonstrating time dilation as a tool for scientific research. Mercury's elliptical orbit precesses, meaning the point of closest approach to the Sun rotates slowly. Classical physics predicts some precession from other planets' gravitational influence. But there's extra precession that classical physics couldn't explain, about 43 arcseconds per century. When Einstein developed general relativity, his equations predicted exactly this extra precession. Part of the explanation involves gravitational time dilation, affecting Mercury at different points in its orbit. When Mercury is closer to the Sun, it's in a stronger gravitational field where time runs slower. This affects the orbital mechanics in ways Newton's theory doesn't capture. The match between Einstein's prediction and the observed precession was one of the first confirmations that general relativity correctly describes gravity. It's a subtle effect requiring decades of careful observations to measure, but it's there. The Parker Solar Probe flies closer to the Sun than any previous spacecraft, diving to within 3.8 million miles of the Sun's center. At perihelion, it experiences strong gravitational time dilation from the Sun's gravity and velocity time dilation from traveling at 120 miles per second. Mission engineers account for these effects when planning trajectories and communication schedules. The probe's clock runs slightly differently than Earth clocks during close approaches. Precise timing is essential for executing gravity assists and ensuring the spacecraft doesn't accidentally fly too close. These are subtle effects measured in microseconds, but modern spacecraft require such precision that relativistic corrections are necessary even for missions within our solar system. Light always travels at 186,000 miles per second. This isn't just fast, it's the maximum speed anything can travel. Reaching this speed would require infinite energy for anything with mass. As particles accelerate in the Large Hadron Collider, they get closer and closer to light speed, but never quite reach it. At 99.9999991% of light speed, adding more energy barely increases velocity. Almost all the energy goes into increasing mass energy rather than speed. The particles become more energetic, but not much faster. This cosmic speed limit prevents paradoxes. If you could travel faster than light, you could theoretically send signals into the past, creating causality violations. The universe doesn't allow this. Light speed is the maximum. Information can't propagate faster. Cause must precede effect in all reference frames. Quantum field theory combines quantum mechanics with special relativity. Particles aren't little balls, but excitations of underlying fields. These fields obey relativistic principles. Time dilation affects quantum processes just as it affects classical ones. Near a black hole's event horizon, quantum fluctuations create particle-antiparticle pairs. Normally, these pairs annihilate almost instantly, but strong gravitational time dilation can separate them before annihilation. One particle falls into the black hole, the other escapes. This is Hawking radiation, predicted by Stephen Hawking in 1974. Hawking radiation means black holes slowly evaporate. A solar mass black hole would take 10 to the 67 years to evaporate. Tiny black holes evaporate faster, A mountain mass black hole would explode in about a billionth of a second, releasing energy equivalent to millions of nuclear bombs. This prediction combines quantum mechanics, general relativity, and time dilation. It's one of the most elegant results in theoretical physics, even though we haven't directly observed it yet. If time passes at different rates for different observers, what does this mean for consciousness and free will? If all of space-time exists as a four-dimensional block, is the future already determined? Relativity shows there's no universal now. Different observers disagree about which events are simultaneous. This challenges the idea that reality has a definite state at each moment that's the same everywhere. Some philosophers argue this supports the block universe view, where past, present, and future all exist equally. We experience space-time one moment at a time, like reading a book, page by page, but all the pages exist. Others argue consciousness and choice operate at a different level than space-time geometry and can't be reduced to physics. These debates continue. What's clear is that our intuitive understanding of time flowing universally from past through present to future doesn't match how the universe actually works. Time is more subtle and strange than everyday experience suggests. Future networks of ultra-precise atomic clocks could test relativity with unprecedented accuracy. Optical clocks at different locations could be compared via fiber optic links, searching for any deviations from predicted time dilation. Such networks might detect gravitational waves through the tiny time dilation changes as waves pass by. They could measure variations in Earth's gravitational field useful for geophysics. They might even detect dark matter if it interacts with normal matter in ways that affect clock rates. Several research groups worldwide are building these capabilities. The next generation of clock networks will test Einstein's theories more precisely than ever before. Any discrepancy, even tiny, could point toward new physics. If intelligent life exists elsewhere in the galaxy, communication would face light-speed delays measured in years. A civilization 40 light-years away would experience an 80-year round trip for messages. You could ask a question and die of old age before receiving an answer. This transforms what communication means. No dialogue or negotiation in real time. Instead, encyclopedic messages containing everything one civilization knows, sent hoping for a reply decades or centuries later. Time dilation makes this even stranger. If a civilization uses relativistic spacecraft, time passes differently for travelers than for people who stay home. A ship traveling at 99.9% of light speed might deliver a message in subjective months, while decades pass for the sender and recipient. The travelers would be out of sync with both civilizations. You might think time dilation only matters for exotic situations like black holes or particle accelerators. But it happens in everyday materials too, just at scales too small to notice without sophisticated equipment. When you heat a metal, the atoms vibrate faster. Each atom is moving, which means each atom experiences tiny amounts of time dilation compared to a stationary reference frame. The effect is absurdly small. At typical thermal velocities, maybe a few hundred meters per second, the Lorentz factor is 1 plus, about 10 to the minus 13. Time runs slower by about 1 part in 10 trillion. You'd never notice this. But in principle, a hot object ages infinitesimally slower than an identical cold object. The hotter object's atoms are moving faster, experiencing more time dilation. This has no practical consequences because the effect is so tiny, but it's there, happening constantly in everything around you. Electrons in current-carrying wires drift at speeds of millimeters per second. they're experiencing time dilation. Again, the effect is completely negligible. But it exists. Every moving particle, every flowing fluid, every spinning object experiences time dilation based on its motion. Even Earth itself experiences time dilation. Earth rotates, meaning every point on the surface is moving. Points at the equator move at about 1,000 miles per hour. This causes time dilation. A clock at the equator runs slightly slower than a clock at the poles, where the rotational velocity is 0. The effect is about 1 part in 10 to the 13th. Completely unmeasurable without atomic clocks. But it's real. Before talking more about time dilation, we should mention how general relativity was first tested. In 1919, Arthur Eddington led an expedition to observe a total solar eclipse. General relativity predicted that the sun's gravity would bend starlight passing near it. This would make stars appear slightly displaced from their actual positions when the sun was nearby in the sky. You can only test this during a total eclipse when stars become visible near the sun. Eddington photographed stars during the eclipse and compared their positions to photographs taken when the sun was elsewhere in the sky. The stars appeared shifted by exactly the amount Einstein predicted. This wasn't a direct test of time dilation, but it confirmed that gravity curves space-time as general relativity describes. If gravity curves space, it also affects time. The two are inseparable in Einstein's framework. Eddington's confirmation made Einstein internationally famous and established general relativity as a serious competitor to Newtonian gravity. In the 1960s, Erwin Shapiro proposed another test of general relativity. Send a radio signal past the sun to a planet or spacecraft on the far side. Measure how long the signal takes to make the round trip. Compare this to the time you'd expect from classical physics. General relativity predicts the signal should take longer than expected because it's traveling through curved space-time near the sun. Space-time curvature makes the path longer and also affects time itself. The extra delay is called the Shapiro time delay. Shapiro tested this by bouncing radar signals off Venus and Mercury when they were nearly behind the sun from Earth's perspective. The signals took about 200 microseconds longer than classical physics predicted, exactly matching Einstein's equations. This has been tested multiple times with increasing precision using spacecraft. The Cassini probe orbiting Saturn provided extremely precise measurements when it passed behind the sun from Earth's viewpoint. Radio signals to and from Cassini showed the exact time delay general relativity predicts. The Shapiro delay is another confirmation that gravity affects time. Signals traveling through regions of curved space-time near massive objects take longer, not just because the path is longer, but because time itself runs differently there. Pulsars are rotating neutron stars that emit beams of radiation from their magnetic poles. As the pulsar rotates, the beams sweep across space like lighthouse beams. If one of these beams points toward Earth, we detect regular pulses as the neutron star rotates. Some pulsars rotate hundreds of times per second with incredible regularity. In 1974, Russell Hulse and Joseph Taylor discovered a pulsar in orbit with another neutron star. This binary pulsar system, designated PSRB 1913+16, provided a new way to test general relativity. As the two neutron stars orbit each other, they emit gravitational waves. These ripples in space-time carry energy away from the system. This loss of energy makes the orbit gradually shrink. The orbital period decreases predictably, according to general relativity. Hulse and Taylor monitored the pulsar for years, measuring the orbital period with extraordinary precision. The pulsar acts like a clock. They found the orbit was indeed shrinking at exactly the rate general relativity predicted for energy loss through gravitational waves. The match was so precise, it left no doubt. This was the first indirect detection of gravitational waves, decades before LIGO directly observed them. It was also another confirmation that general relativity correctly describes gravity and its effects on time and space. Hulse and Taylor won the Nobel Prize in Physics in 1993 for this discovery. Light from the sun shows gravitational redshift. Photons climbing out of the sun's gravitational well lose energy. Their wavelength increases, shifting toward the red end of the spectrum. This effect is small but measurable. Spectral lines from elements in the sun's atmosphere appear at slightly different wavelengths than the same elements in laboratories on Earth. The sun's lines are shifted toward longer wavelengths by exactly the amount general relativity predicts based on the sun's mass and radius. This is gravitational time dilation, manifesting in light from the sun. Time runs slower in the sun's stronger gravitational field. Atoms vibrating in the sun's atmosphere oscillate more slowly from our perspective. Their emitted light has a lower frequency and longer wavelength. This has been measured with high precision using solar spectroscopy. The observations match the theoretical predictions. It's one more confirmation that gravity affects time exactly as Einstein described. Chemical reaction rates depend on molecular collision rates and energies. If time is running slower, reactions proceed more slowly from an external observer's perspective. In a strong gravitational field or at high velocity, chemistry happens at a different rate. For everyday situations, this effect is completely negligible. But in principle, chemistry near a black hole would proceed more slowly than chemistry far away. Molecules near the event horizon would react more slowly. Their chemical processes would appear to run in slow motion. Similarly, chemistry on board a spacecraft traveling at 99% of light speed would appear slowed down by a factor of 7 from the perspective of stationary observers. The molecules themselves wouldn't notice anything unusual. In their reference frame, reactions proceed normally. But external observers see molecular motion and chemical transformations happening in slow motion. This applies to all chemical processes, including biochemistry. Biological aging is fundamentally chemistry. DNA replication, protein synthesis, metabolism, all of it is chemistry. Time dilation slows these processes from an external perspective, which is why travelers on fast spacecraft age more slowly. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the light's path bends due to space-time curvature. This creates gravitational lensing effects. The background galaxy appears distorted, sometimes forming multiple images, or even complete rings called Einstein rings. Gravitational lensing is related to time dilation. The light is traveling through curved space-time, where time runs at different rates, depending on proximity to the massive object. The curvature that bends the light's path is the same curvature that affects time. Astronomers use gravitational lensing to map dark matter in galaxy clusters. Dark matter doesn't emit light, but it has mass and therefore curves space-time. By observing how background galaxies are lensed, astronomers can infer the distribution of mass in the foreground cluster, including the dark matter we can't see directly. This is another practical application of general relativity. Understanding how gravity curves space-time and affects light propagation lets us map the universe's large-scale structure. Imagine a simple clock made from two mirrors with a photon bouncing between them. Each bounce marks one tick. This is called a light clock. Light clocks help visualize how time dilation works. If you carry a light clock on a fast-moving train, the photon's path appears diagonal from the platform observer's perspective. The photon has to travel a longer distance between bounces because the mirrors are moving. But light always travels at the same speed. The only way for the photon to cover more distance at the same speed is if more time passes. The clock ticks slower from the platform observer's perspective. From your perspective on the train, the photon bounces straight up and down between stationary mirrors. Your clock ticks normally. Both observers are correct in their own reference frames. The difference arises because they're measuring different paths through space-time. Space-time is four-dimensional, 3 space dimensions plus 1 time dimension. Events are points in space-time. The interval between 2 events is like a distance in this 4-dimensional space. Different observers slice space-time into space and time differently, but they all agree on space-time intervals. This geometry underlies all of relativity. Time dilation isn't a mysterious force acting on clocks. It's a consequence of how space-time geometry works. Moving through space changes your path through space-time, which affects how you experience time. The Doppler effect normally refers to frequency shifts when a source moves toward or away from you. An ambulance siren sounds higher-pitched approaching and lower-pitched receding. This is the longitudinal Doppler effect. But relativity predicts a transverse Doppler effect. Even when a source moves perpendicular to your line of sight, neither approaching nor receding, its light is redshifted due to time dilation. The source's clock is running slow from your perspective. Its light has a lower frequency than expected. This has been measured using particle beams. Particles moving perpendicular to the detector emit light that's redshifted by exactly the amount time dilation predicts. There's no classical Doppler effect because the particles aren't moving toward or away from the detector. The shift is purely relativistic, caused by time dilation. The transverse Doppler effect provides another independent confirmation that moving clocks run slow. It's a direct observation of time dilation through frequency shifts that have no classical explanation. Modern spectroscopy can measure atomic transition frequencies with extraordinary precision. Comparing frequencies for atoms at rest versus atoms in motion provides direct tests of time dilation. Researchers accelerate ions to known velocities and measure their spectral lines. The lines are shifted by exactly the amount the Lorentz factor predicts. These measurements reach precisions better than 1 part in 10 to the 15th. The theory and observations match perfectly across more than 15 orders of magnitude in precision. This represents some of the most precise tests of special relativity ever conducted. Any deviation would show up at these precision levels. None has ever been found. Time dilation works exactly as Einstein's equations describe. Earth's gravity causes clocks at different altitudes to run at different rates. This isn't just a curiosity. It has practical implications for precision timing networks. The International Atomic Time Standard is based on clocks at sea level. Clocks at higher elevations run faster. A clock at 1,000 feet elevation gains about 30 nanoseconds per day compared to sea level. A clock at 10,000 feet gains about 300 nanoseconds per day. For applications requiring extreme timing precision, like synchronizing financial transactions or coordinating distributed scientific experiments, these effects matter. Timing networks must account for the altitude of each clock to maintain synchronization. Future quantum networks for secure communication will use entangled photons distributed through fiber optic cables. Time synchronization between network nodes will be essential. Gravitational time dilation from altitude differences will need correction to keep the network functioning. Einstein built general relativity on the equivalence principle, which states that gravity and acceleration are indistinguishable locally. If you're in a windowless room, you can't tell whether you're sitting on Earth, experiencing gravity, or in a rocket in deep space accelerating at 1g. This principle implies that acceleration must cause time dilation, just like gravity does. If gravitational time dilation is real and acceleration is equivalent to gravity, then acceleration must dilate time too. This has been tested. Particles in circular accelerators are constantly accelerating as they curve around the ring. Their clocks run slow not just from their velocity, but also from their acceleration. The combined effect matches the predictions. The equivalence principle is fundamental to general relativity. Every test that confirms gravitational time dilation also supports the equivalence principle. The two are inseparable. The Laser Interferometer Gravitational Wave Observatory detected gravitational waves directly for the first time in 2015. Gravitational waves are ripples in space-time itself, traveling at light speed. When a wave passes by, it stretches space in one direction, while compressing it perpendicular to that direction. LIGO detects these stretches and compressions by measuring tiny changes in the distance between mirrors using laser interferometry. The first detection came from two black holes merging about 1.3 billion light-years away. As the black holes spiraled together and merged, they emitted gravitational waves that eventually passed through Earth. Gravitational waves carry information about extreme space-time curvature. The merging black holes created regions where time dilation was enormous. The waves preserve information about these extreme conditions. By detecting and analyzing gravitational waves, we learn about the most extreme gravitational environments in the universe. LIGO has now detected dozens of mergers involving black holes and neutron stars. Each detection teaches us more about how gravity works at its strongest. This is observational general relativity, testing Einstein's theory in regimes far beyond what's possible in our solar system. The electrons in atoms move at speeds determined by quantum mechanics. In heavy elements like gold, inner electrons orbit at significant fractions of light speed. These electrons experience measurable time dilation. This affects atomic properties. Gold appears yellowish, partly because of relativistic effects on its electrons. The time dilation they experience shifts energy levels, changing which wavelengths of light the atoms absorb and reflect. Without relativistic corrections, models of gold's optical properties don't match observations. Similarly, mercury is liquid at room temperature partly because of relativistic effects. The time dilation experienced by mercury's electrons affects the bonding between atoms, weakening the bonds enough that mercury remains liquid while similar elements are solid. These aren't dramatic effects, but they're real and measurable. Chemistry and atomic physics require relativistic corrections for heavy elements. Time dilation affects the behavior of atoms themselves. Muonium is an exotic atom consisting of a positive muon and an electron. It's like hydrogen, but with a muon instead of a proton. Muonium atoms decay quickly because muons are unstable. Scientists can create muonium atoms at high velocities and study their properties. The atom's lifetimes are extended by time dilation. Spectroscopy of fast-moving muonium atoms shows frequency shifts matching the predictions for time dilation combined with the transverse Doppler effect. Muonium provides another system for precision tests of relativity. The atoms are simple enough to calculate their properties accurately. Measurements can test theory with high precision. So far, all observations match the predictions perfectly. Lorentz invariance is the principle that the laws of physics are the same in all inertial reference frames. Time dilation is a consequence of Lorentz invariance combined with the constancy of light speed. Any violation of time dilation would indicate a breakdown of Lorentz invariance. Physicists have designed extremely sensitive tests searching for violations. So far, none has been found. The tests reach sensitivity levels of parts in 10 to the 18th or better. This means if Lorentz invariance is violated, the violation is smaller than 1 part in a trillion. Some theories of quantum gravity predict tiny violations of Lorentz invariance. Finding such violations would be revolutionary, pointing toward new physics beyond general relativity and the Standard Model. The null results so far don't rule out violations entirely, but they severely constrain any possible effects. Charged particles moving in magnetic fields emit electromagnetic radiation. In circular accelerators, this is called synchrotron radiation. The radiation pattern and intensity depend on the particle's energy and velocity. At high energies, where particles are traveling close to light speed, time dilation affects the radiation. The particles are effectively living in slow motion from our perspective. This changes how they radiate. The observed radiation spectrum matches calculations that include time dilation effects. Synchrotron facilities produce intense beams of X-rays and other radiation for scientific research. Understanding how particles radiate requires accurate relativistic calculations, including time dilation. The facilities work as designed because the theory is correct. Particles in magnetic fields spiral in helical paths. The rotation frequency depends on the particle's charge to mass ratio. For particles moving at relativistic speeds, time dilation affects this rotation frequency. The cyclotron frequency for a particle at rest is proportional to its charge divided by its mass. For a relativistic particle, the effective mass increases by the Lorentz factor. The cyclotron frequency decreases proportionally. Measurements of particle trajectories in magnetic fields confirm this effect. This is important for particle accelerators and detectors. Calculating particle paths through magnetic fields requires accounting for relativistic mass increase and time dilation. Without these corrections, particles wouldn't end up where predicted. Earth orbits the Sun, which orbits the galactic center. We're in the Milky Way's gravitational field. This causes time dilation compared to a hypothetical observer in intergalactic space, far from any galaxies. The effect is small, roughly 1 part in a million. Clocks in intergalactic voids run about 1 millionth faster than clocks in galaxies. This has no practical consequences for us, but it means time genuinely passes at slightly different rates depending on where you are in the universe. In dense galaxy clusters, where multiple galaxies' gravitational fields overlap, time dilation is greater. Clocks in cluster centers run slower than clocks in the sparse regions between clusters. On cosmic scales, the distribution of matter creates a landscape of varying time dilation throughout the universe. Many stars exist in binary systems where 2 stars orbit their common center of mass. The stars experience gravitational time dilation from each other's mass and velocity time dilation from their orbital motion. For close binaries where stars orbit rapidly, these effects are measurable. Spectroscopic observations can detect time dilation through frequency shifts in the star's light. The observations match theoretical calculations based on the star's masses and orbital parameters. Binary systems provide natural laboratories for testing relativity. No laboratory on Earth can create two massive objects orbiting each other at significant fractions of light speed. But nature does this constantly. Binary pulsars, binary white dwarfs, and binary black holes all demonstrate relativistic effects in their orbital dynamics. General relativity predicts that black holes are remarkably simple objects, characterized completely by three properties: mass, electric charge, and angular momentum. This is the no-hair theorem. All other information about the matter that formed the black hole is lost. Time dilation is integral to understanding this. As matter falls into a black hole, from an external observer's perspective, it freezes at the event horizon due to infinite time dilation. The information about the matter's internal structure effectively disappears, leaving only the three conserved quantities. This has led to debates about information conservation in quantum mechanics. If information truly disappears into black holes, it violates quantum mechanical principles. Stephen Hawking and others have argued about whether information is genuinely lost. The resolution likely involves understanding how quantum mechanics and general relativity fit together, which we don't fully know yet. The second law of thermodynamics states that entropy always increases. Entropy is often interpreted as disorder or the number of possible microscopic states. Time's arrow, the fact that we experience past and future as distinct, might be connected to entropy increase. But if time itself runs at different rates, how does this affect entropy? Does a system in a strong gravitational field where time runs slow have entropy that increases more slowly from an external observer's perspective? These questions touch on deep issues in physics. Entropy is a statistical concept based on counting states. If time dilation changes the rate at which processes occur, it affects how quickly a system explores its state space. This could have implications for understanding thermodynamics in curved spacetime. Black hole thermodynamics, developed by Jacob Bekenstein and Stephen Hawking, shows that black holes have entropy proportional to their event horizon area. The extreme time dilation at the event horizon is fundamental to these arguments. Understanding black hole entropy requires understanding how time dilation affects thermodynamic processes. In relativity, we distinguish between proper time and coordinate time. Proper time is what a clock measures following a specific path through spacetime. Coordinate time is time in some chosen reference frame. For example, in the twin paradox, proper time is what each twin's watch shows. The traveling twin's watch shows less elapsed time than the Earth twin's watch. Both are measuring proper time along their respective paths through spacetime. Coordinate time is more arbitrary. You can choose different coordinate systems to describe the same events. In one coordinate system, events might appear simultaneous. In another coordinate system, the same events occur at different times. But proper time is invariant. All observers agree on what a specific clock reads. This distinction is crucial for understanding general relativity. The geometry of spacetime determines relationships between proper times along different paths. Time dilation arises because different paths through spacetime accumulate different amounts of proper time between the same two events. Spacetime diagrams plot space horizontally and time vertically. Events are points. World lines representing objects' histories are curves. Light travels at 45-degree angles, since it moves 1 light second through space per second of time. Time dilation becomes geometrically visible on space-time diagrams. A moving object's world line is tilted compared to a stationary object. The tilt represents velocity. Lines of simultaneity for the moving observer are tilted relative to the stationary observer's simultaneity lines. This visualizes why different observers disagree about which events are simultaneous. Gravitational time dilation appears as the space-time geometry becoming curved rather than flat. Near a massive object, world lines curve and the geometry warps. Light follows curved paths. Time dilation corresponds to how the geometry stretches time differently at different locations. These diagrams aren't just illustrations. They're powerful tools for understanding relativity. Complex problems become clearer when you visualize them in space-time rather than thinking about space and time separately. Time dilation has a companion effect called length contraction. Objects moving at high speed are contracted in the direction of motion from a stationary observer's perspective. This isn't a physical compression. It's a consequence of how different observers slice space-time into space and time. For muons falling through the atmosphere, we explain their survival using time dilation from our perspective. From the muon's perspective, time passes normally, but the atmosphere appears contracted. The 9-mile thick atmosphere becomes about 2 miles thick at 98% of light speed. The muon can traverse the contracted distance in its short lifetime. Both explanations are equally valid. Time dilation and length contraction are two aspects of the same relativistic phenomenon. How you describe what happens depends on your reference frame, but the physical outcome is the same. Length contraction has been verified indirectly through the same experiments that confirm time dilation. You can't easily measure the length of a fast-moving particle directly, but you can measure its lifetime and trajectory. The observations are consistent only if length contraction occurs exactly as the theory predicts. In classical physics, momentum equals mass times velocity. In relativity, momentum includes the Lorentz factor. Relativistic momentum equals the Lorentz factor times mass times velocity. As velocity approaches light speed, momentum grows without bound, even though velocity asymptotically approaches a limit. This is why accelerating particles at the LHC requires such enormous energy. The particles are already traveling at 99.99999% of light speed. Adding more energy increases their momentum and the Lorentz factor, but barely affects velocity. The particles gain energy and therefore effective mass, but don't go much faster. Relativistic momentum conservation is essential for understanding particle collisions. Detectors at the LHC measure particle trajectories after collisions. Analyzing these trajectories requires relativistic momentum formulas. Classical momentum wouldn't conserve. The observations match relativistic calculations precisely. Einstein's equation E equals mc squared states that mass and energy are equivalent. This is deeply connected to time dilation and the structure of spacetime. The full energy-momentum relation is E squared equals P squared C squared plus M squared C to the fourth, where E is energy, P is momentum, M is rest mass, and C is light speed. For a particle at rest, momentum is 0 and E equals mc squared. For a massless particle, like a photon, rest mass is 0 and E equals pc. For particles moving at intermediate velocities, both terms contribute. The Lorentz factor appears in the energy formula. Total energy equals the Lorentz factor times rest mass times c squared. As velocity increases, The Lorentz factor increases, and so does energy. The particle isn't gaining rest mass. It's gaining kinetic energy, but that energy contributes to the particle's inertia and behaves like mass in gravity and collisions. This unification of mass and energy underlies nuclear reactions, particle physics, and cosmology. It's also intimately connected to time dilation. The same Lorentz factor that determines time dilation also determines energy and momentum at relativistic speeds. Millisecond pulsars are neutron stars rotating hundreds of times per second with incredible stability. They're natural clocks with precision rivaling atomic clocks. Some pulsars are in binary systems with white dwarfs or other neutron stars. These systems let astronomers test general relativity in strong gravitational fields. The neutron star's pulse arrival times are affected by several relativistic effects. Shapiro delay as pulses pass through the companion's gravitational field. Gravitational redshift from the neutron star's intense gravity. Orbital precession from space-time curvature. By carefully timing pulses over months or years, astronomers measure these effects with extraordinary precision. The observations match general relativity's predictions to within fractions of a percent. This tests the theory in gravitational fields billions of times stronger than Earth's. The double pulsar system, PSR J0737-3039, is particularly valuable. Both neutron stars in the system are pulsars, providing two independent clocks orbiting each other at high speed in strong gravity. This system has enabled the most precise tests of general relativity outside the solar system. When pulses from a pulsar pass close to its companion star, they experience Shapiro delay. The strong gravitational field near the companion curves space-time, making pulses take longer to reach us. This delay varies as the pulsar orbits its companion. By measuring how the pulse arrival times change throughout the orbit, astronomers can determine the companion's mass and the orbital geometry. The measurements precisely match general relativity's predictions. Any deviation would indicate problems with the theory. The Shapiro delay in pulsar systems can be microseconds to milliseconds, depending on the orbital inclination and companion mass. For edge-on systems, where pulses pass very close to the companion, the delay is largest and easiest to measure. These measurements test general relativity in regimes inaccessible to solar system experiments. The gravitational fields are much stronger, the velocities are much higher. The agreement between theory and observation confirms that general relativity works even in these extreme conditions. Gravity Probe B was a NASA satellite launched in 2004 to measure frame dragging near Earth. The satellite carried 4 gyroscopes, spinning spheres that should point in fixed directions unless disturbed. General relativity predicts Earth's rotation drags space-time around with it. This frame dragging should cause the gyroscope's orientations to drift slightly over time. The predicted drift was tiny, about 39 milliarc-seconds per year, less than the width of a human hair viewed from 10 miles away. After years of data analysis to remove confounding effects, the Gravity Probe B team confirmed frame dragging at about 80% of the predicted value. The uncertainty was large enough that the measurement was consistent with general relativity within error bars. This was the first direct measurement of frame dragging on Earth. Previous tests had come from analyzing satellite orbits, which showed indirect evidence. Gravity Probe B directly detected the effect through gyroscope precession. Frame dragging is important for understanding rotating black holes and neutron stars. Near these objects, frame dragging is extreme. Ergospheres form where you can't avoid being dragged around. Understanding these regions requires understanding frame dragging, which is a prediction unique to general relativity not present in Newtonian gravity. Frame dragging creates effects analogous to magnetic fields in electromagnetism. Moving charges create magnetic fields. Moving or rotating mass creates gravitomagnetic fields. These fields affect moving objects, causing precessions and orbital perturbations. Earth's gravitomagnetic field is weak but measurable. Satellite orbits show tiny perturbations attributable to gravitomagnetism. The largest satellites, passive metal spheres covered in retroreflectors, have orbits tracked with millimeter precision. Their orbital precession matches general relativity's gravitomagnetic predictions. Near black holes and neutron stars, gravitomagnetic effects are strong. They affect how matter accretes onto these objects. Accretion disks can become tilted and precess due to gravitomagnetic forces. Jets launched from near black holes might be channeled by gravitomagnetic fields. Understanding gravitomagnetism requires understanding how moving mass curves space-time. This is intimately related to time dilation because motion and gravity both arise from space-time geometry in general relativity. Gravitomagnetic effects and time dilation are different manifestations of the same underlying curved space-time. Observations of distant supernovae in the late 1990s revealed that the universe's expansion is accelerating. Some mysterious dark energy is pushing space apart, overcoming gravity's attraction. This discovery won the Nobel Prize in Physics in 2011. Cosmological time dilation plays a role in these observations. Distant supernovae appear to brighten and fade more slowly than nearby ones due to the expansion of space stretching out time. Measuring this time stretching precisely requires accounting for cosmic acceleration. The combination of distance measurements and time dilation observations lets cosmologists determine how the expansion rate has changed over time. This reveals the influence of dark energy. Without accurate time dilation measurements, we wouldn't have discovered cosmic acceleration. Dark energy remains mysterious. We don't know what it is or why it exists, but its effects on the universe's expansion are real and measurable through precise observations that account for both spatial expansion and cosmological time dilation. The next generation of atomic clocks will be accurate to 1 second in the age of the universe or better. Networks of such clocks could test general relativity with unprecedented precision. They could search for variations in fundamental constants, detect gravitational waves, and map Earth's gravitational field with incredible detail. Portable optical clocks might fly on satellites, enabling space-based tests of relativity. Clocks at different altitudes in Earth orbit would experience different gravitational potentials. Comparing their rates would test gravitational time dilation more precisely than ever before. Clocks on missions to the outer solar system could test general relativity far from the Sun. Does gravitational time dilation work the same everywhere? Do the equations hold in the weak fields of distant space? So far, there's no reason to doubt it, but precise tests would confirm. Eventually, clocks might accompany missions to other stars if we develop interstellar propulsion. Clocks traveling at relativistic speeds would directly demonstrate time dilation on macroscopic objects over long journeys. This would be the ultimate confirmation of special relativity's predictions about time. Beyond GPS, other satellite navigation systems exist worldwide. GLONASS from Russia, Galileo from Europe, Beidou from China, all face the same relativistic challenges as GPS. All must correct for time dilation or they wouldn't function accurately. Each system has satellites in different orbits at different altitudes. The relativistic corrections differ slightly between systems. GLONASS satellites orbit at about 12,000 miles altitude. Galileo satellites orbit at about 14,300 miles. Beidou uses multiple orbital planes at different altitudes. Each system requires custom calculations for its specific orbital parameters. Engineers designing these systems must understand general and special relativity thoroughly. A mistake in the relativistic corrections would cause navigation errors. The satellites would drift out of sync. Positions calculated by receivers would be wrong. The entire system would fail. The fact that all these navigation systems work as designed confirms relativity works exactly as predicted. Billions of people use these systems daily. Cars, phones, airplanes, ships, farm equipment, survey instruments, all rely on satellites that account for time dilation. This is relativistic physics in your pocket. When matter falls into a black hole, what happens to information about its quantum state? Quantum mechanics says information can't be destroyed. But from an external observer's perspective, matter falling into a black hole freezes at the event horizon due to infinite time dilation. Then, Hawking radiation slowly evaporates the black hole over immense timescales. Does the information escape in the radiation, or is it lost? This information paradox has puzzled physicists for decades. Stephen Hawking initially argued information is lost, violating quantum mechanics. Later he changed his view, suggesting information is encoded in the Hawking radiation somehow. The debate continues. Time dilation is central to this puzzle. The infinite time dilation at the event horizon means an external observer never sees matter actually cross into the black hole. From the falling matter's perspective, crossing is smooth and quick. These incompatible descriptions lead to questions about what's fundamentally real and where information resides. Resolution might require understanding quantum gravity, a theory combining general relativity and quantum mechanics that we don't yet have. Time dilation and space-time geometry must somehow fit together with quantum information in ways we're still working out. Many black holes and neutron stars launch jets of particles at close to light speed. These jets can extend for millions of light years, visible across cosmic distances. The particles in these jets experience extreme time dilation. From our perspective, particles in a jet moving at 99.99% of light speed are aging very slowly. They can travel enormous distances before decaying or losing energy. This helps explain how jets maintain their coherence over such vast scales. The jets also experience beaming effects from relativistic motion. Radiation from particles moving toward us is blue shifted and brightened. Radiation from particles moving away is red shifted and dimmed. This creates asymmetries in what we observe. Jets pointed toward Earth appear much brighter than those pointed away. Understanding relativistic jets requires understanding time dilation, length contraction, Doppler effects, and space-time curvature near the launching regions. It's a rich application of relativity to real astrophysical phenomena. Cosmologists run computer simulations of galaxy formation and cosmic evolution. These simulations must account for the expansion of space and its effect on time. As space expands, the relationship between physical distances and coordinate distances changes. Time dilation enters through the cosmological redshift. Simulations track billions of particles representing dark matter and gas over cosmic time. The particles experience gravitational time dilation from nearby mass concentrations. They also experience cosmological time dilation from living in an expanding universe. Both effects must be included for accurate results. Modern cosmological simulations, like Illustris TNG, reproduce the large-scale structure of the universe with remarkable fidelity. Galaxies, clusters, voids, filaments all emerge from simulations that properly account for relativistic effects, including time dilation. This is computational general relativity applied to the entire observable universe. Strong gravitational lensing creates obvious multiple images of background galaxies. Weak gravitational lensing causes subtle shape distortions. Both involve light traveling through curved spacetime, where time dilation varies. Light taking different paths through the gravitational lens can arrive at different times due to varying time dilation along the paths. This time delay can be measured for variable sources like quasars. The different images of the quasar brighten and fade at different times due to the extra path length and time dilation along different routes. Measuring these time delays lets astronomers determine the mass distribution in the lensing galaxy or cluster. It also provides an independent way to measure the Hubble constant, the universe's expansion rate. Time delays combined with geometric modeling give distance estimates that don't rely on standard candles or rulers. This technique, called time delay cosmology, is an active research area. Precision measurements of gravitational lens time delays are helping resolve disagreements about the Hubble constant measured different ways. Time dilation becomes a tool for cosmology. Distant galaxies show redshift from the expansion of space. Light leaving a distant galaxy is stretched as space expands during the light's journey to us. When we receive the light, its wavelength is longer and its frequency is lower than when emitted. This redshift isn't a Doppler shift from motion through space, it's cosmological redshift from space itself expanding. But it's closely related to time dilation. An observer in the distant galaxy experiences time differently than we do, because we're separated by expanding space. The redshift tells us how much the universe has expanded since the light was emitted. A redshift of 1 means the universe has doubled in size. Redshift of 2 means tripled. The highest redshift galaxies detected have redshifts above 10, meaning the universe has expanded more than tenfold since their light left. This expansion history reveals how time dilation has affected cosmic evolution. Structure formation, star formation, galaxy mergers all happened at rates affected by cosmological time dilation. Understanding the early universe requires understanding how time dilation worked when space was denser and expansion was faster. Since the Apollo missions left retroreflectors on the Moon, scientists have bounced laser pulses off them to measure the Earth-Moon distance with millimeter precision. These measurements test general relativity by tracking how Earth and Moon move in the Sun's curved spacetime. The laser travel times include effects from gravitational time dilation. Light traveling from Earth to the Moon and back passes through regions with different gravitational potentials. The round-trip time depends on both distance and the varying time dilation along the path. Decades of lunar laser ranging data have tested general relativity's predictions for gravitational time dilation and the equivalence principle. The Moon's orbit shows no deviations from general relativity. Time dilation matches predictions to within experimental uncertainty. This test is sensitive because the measurements are extraordinarily precise and have accumulated over decades. Any tiny deviation from general relativity would show up as a systematic drift in the data. None has been detected. Some alternative theories to general relativity predict violations of Lorentz invariance. These violations would create a preferred reference frame where physics works differently. Time dilation might depend on absolute velocity relative to this frame rather than relative velocity between observers. Extensive searches for preferred frame effects have found nothing. Particle physics experiments, atomic spectroscopy, GPS observations, all are consistent with standard relativity where there's no preferred frame. If a preferred frame exists, its effects are smaller than current experimental sensitivity. These null results strongly constrain alternative theories. General relativity remains consistent with all observations. Future experiments with even higher precision will continue testing, but so far Einstein's framework shows no cracks. Comparing atomic clocks at different locations tests both special and general relativity. Modern optical clocks are precise enough to detect time dilation from height differences of inches or velocity differences of feet per second. Researchers have transported clocks between laboratories, flown them on aircraft, and compared clocks via fiber optic links. Every comparison shows time dilation exactly matching predictions. Clocks at higher altitude run faster. Clocks moving faster run slower. The effects combine as general and special relativity predict. These experiments use the best clocks humanity can build. The measurements probe relativity with precision better than 1 part in 10 to the 18th. This is testing physics at extreme limits. The theory works perfectly across more than 18 orders of magnitude. The fine structure constant determines the strength of electromagnetic interactions. It's a dimensionless number approximately equal to 1 over 137. Some theories suggest this constant might vary slowly over cosmic time. Ultra-precise atomic clocks can search for variations in the fine structure constant. If it changes, different atomic transitions would shift by different amounts. By comparing clocks based on different transitions, you can detect even tiny variations. So far, no variation has been found. The fine structure constant appears to be genuinely constant, at least to the precision we can currently measure. This constrains theories that predict variation and supports the idea that fundamental constants are truly fundamental and unchanging. In heavy atoms, inner electrons orbit at speeds approaching significant fractions of light speed. For gold, the innermost s electrons move at about 60% of light speed on average. At this velocity, time dilation and relativistic mass effects become noticeable. These relativistic effects shift atomic energy levels. Chemical properties depend on energy levels. Gold's chemistry is affected by relativistic effects on its electrons. The yellow color of gold is partly due to relativistic corrections shifting which wavelengths are absorbed. Calculations of heavy element properties require relativistic quantum mechanics. Non-relativistic calculations give wrong answers. This is practical chemistry requiring Einstein's relativity for accurate predictions. Electrons have spin, an intrinsic angular momentum. Orbit refers to their motion around the nucleus. Spin and orbit interact through relativistic effects, including time dilation experienced by the electron as it moves. This spin-orbit coupling affects atomic spectra, creating fine structure in spectral lines. The strength of spin-orbit coupling increases with atomic number because inner electrons in heavy atoms move faster and experience more time dilation. Measuring atomic spectra precisely tests relativistic quantum mechanics. The observations match theoretical predictions that include time dilation and other relativistic corrections. This is another regime where relativity affects everyday matter. GPS signals don't just need precise clocks. Signal propagation through the atmosphere must also be modeled accurately. Atmospheric refraction bends signals. Ionospheric delays affect transmission times. All of this must be corrected along with relativistic effects. The signals travel at light speed, which is constant, but the atmosphere affects the effective speed. Engineers model these effects to maintain GPS accuracy. Combined with relativistic time dilation corrections, the complete system achieves meter-level positioning accuracy. This is systems engineering meeting fundamental physics. You can't separate the practical from the theoretical. GPS works because engineers understand both atmospheric physics and general relativity. Remove either, and the system fails. Mercury's orbit precesses due to general relativistic effects. Other planets show similar precession, but smaller because they're farther from the Sun, where space-time curvature is weaker. Binary pulsars show enormous precession rates because their gravity is so much stronger. The precession comes from a combination of factors, including gravitational time dilation affecting different parts of the orbit. When a planet is closer to the Sun, time runs slower, affecting the orbital dynamics in ways Newtonian gravity doesn't predict. Precise measurements of planetary orbits confirm general relativistic precession. The effects are small but measurable. They've been verified for Mercury, Venus, Earth, and other solar system bodies. Every measurement agrees with Einstein's theory. Light from stars appears to come from slightly different directions as Earth orbits the Sun. This is stellar aberration, caused by the combination of light's velocity and Earth's orbital motion. It's like how rain appears to come from ahead when you're driving, even though it's falling straight down. Stellar aberration was discovered long before relativity, but relativistic corrections are needed for precise measurements. Earth's orbital velocity is about 18 miles per second. At this speed, time dilation affects how aberration works at the level of precision modern astrometry achieves. The Gaia spacecraft measures stellar positions with micro-arc-second precision. At this level, relativistic corrections to aberration matter. The satellite's data processing includes these corrections. The resulting star catalog depends on general relativity being correct. The observable universe has a finite size, not because space ends, but because light has had finite time to reach us. There's a cosmological horizon beyond which we cannot see. This horizon is related to time dilation in an expanding universe. As space expands, distant regions recede. Eventually they recede faster than light can propagate through expanding space. This doesn't violate relativity because the regions aren't moving through space faster than light. Space itself is expanding. Light from regions beyond our horizon will never reach us no matter how long we wait. The expansion pushes them away faster than light can close the gap. We're causally disconnected from those regions. Time dilation and spatial expansion combine to create fundamental limits on what we can observe. Hawking radiation lets black holes evaporate. The evaporation rate depends on the black hole's mass. Smaller black holes evaporate faster. Primordial black holes with masses less than billions of tons would have evaporated already. The calculation of evaporation rates requires understanding time dilation near the event horizon and quantum field theory in curved spacetime. It's a tour de force of theoretical physics, combining general relativity, quantum mechanics, and thermodynamics. Large black holes evaporate incredibly slowly. A solar mass black hole takes about 10 to the 67 years. Supermassive black holes take even longer. In our current universe, black holes gain mass faster from absorbing cosmic microwave background radiation than they lose from Hawking evaporation. They're growing, not shrinking. In the far future, after stars burn out and the universe becomes much colder, black holes will begin genuinely evaporating. Eventually, in the unimaginably distant future, even supermassive black holes will disappear in final bursts of radiation. Time dilation at their event horizons is crucial to understanding this process. Quantum entanglement creates correlations between particles that persist regardless of distance. Measuring one entangled particle instantly affects the other, even if they're separated by light years. This seems to violate relativity's prohibition on faster-than-light information transmission. Actually, there's no contradiction. The correlations are real, but you can't use them to send information faster than light. You can't control what result you get when measuring your particle. The correlations only become apparent when you compare results sent through normal channels at light speed or slower. Time dilation doesn't affect entanglement directly, but it does affect how measurements are coordinated. If one observer is experiencing extreme time dilation, they and a distant partner age at different rates. Their measurements occur at times related through time dilation effects. Combining quantum mechanics with curved space-time is challenging. Quantum field theory in curved space-time makes predictions like Hawking radiation, but a complete theory of quantum gravity that fully unifies quantum mechanics and general relativity remains elusive. Objects in free fall follow geodesics, the straightest possible paths through curved space-time. These paths minimize proper time in a technical sense. Understanding geodesics is essential for understanding how time dilation affects trajectories. Earth orbits the Sun following a geodesic through space-time curved by the Sun's mass. The orbit looks curved in space, but it's straight in space-time. Planets aren't pushed by forces. They're following the natural geometry. Gravitational time dilation arises because different paths through space-time accumulate different proper times. A clock deep in a gravitational well ticks slower than a clock farther away because the space-time geometry is more curved. Both clocks are following geodesics, but the geodesics accumulate different proper time. This geometric picture makes time dilation less mysterious. Time isn't arbitrarily slowing down. Different paths through curved space-time naturally have different lengths in the time direction, just as different routes between cities have different spatial lengths. The Shapiro delay is named after Erwin Shapiro, who predicted it in 1964. Radar signals sent past the Sun to planets or spacecraft take longer to return than expected from simple geometry. The extra delay comes from curved spacetime near the Sun, affecting signal propagation. Shapiro delays have been measured for Venus, Mercury, Mars, and various spacecraft. All observations match general relativity's predictions precisely. These tests probe the theory in the Sun's gravitational field across different distances and geometries. The Cassini spacecraft provided exceptional Shapiro delay measurements when it passed behind the Sun from Earth's viewpoint. The radio signals showed delays matching general relativity to better than 1 part in 100,000. This is one of the most precise tests of general relativity in the solar system. Spacecraft trajectories through the solar system test general relativity continuously. The spacecraft must reach their destinations accurately. Their paths depend on gravity working exactly as the theory predicts. The Voyager spacecraft have been traveling for decades. Their trajectories have been tracked precisely. They're now in interstellar space, but still responding to the solar system's gravity. Their paths show no deviations from general relativity. The New Horizons mission to Pluto required extreme precision. Any error in gravitational modeling would cause the spacecraft to miss its target. The successful flyby demonstrates that general relativity correctly predicts gravity's effects even at the edge of the solar system. Magnetars are neutron stars with magnetic fields trillions of times stronger than Earth's. These extreme magnetic fields affect space-time geometry through the stress energy they contain. This alters gravitational time dilation, slightly compared to a neutron star with weaker fields. The effect is small, but potentially measurable. Observations of magnetar emissions might reveal signatures of how extreme magnetic fields affect space-time curvature. This would test general relativity in a regime impossible to create in laboratories. Magnetic fields also affect light propagation through birefringence, creating polarization effects. Combining these with time dilation effects creates complex observational signatures that encode information about the magnetar's properties. When two neutron stars merge, they create extreme gravitational conditions. Gravitational waves from the merger encode information about space-time curvature during the event. Time dilation is severe throughout the merger process. LIGO and Virgo have detected neutron star mergers. One event, GW170817, produced both gravitational waves and electromagnetic radiation. Telescopes worldwide observed the optical, X-ray, and gamma-ray emission from the merger. Analyzing these observations requires understanding time dilation and space-time dynamics during the merger. The gravitational wave signal shows how space-time geometry evolved. Electromagnetic observations show the physical processes creating light. Together, they test general relativity in extreme conditions. Large-scale structure in the universe formed through gravitational instability, amplifying tiny initial density fluctuations. Simulations of this process must account for the expanding universe and cosmological time dilation. As structure collapses and galaxies form, time dilation from concentrations of mass becomes important. The cause of galaxy clusters where time runs slower than in surrounding voids. These effects are small, but accumulate over cosmic time. Modern simulations, like the Millennium Simulation and Illustris TNG, track billions of particles over the universe's history. They reproduce the observed large-scale structure remarkably well. This success demonstrates that we understand cosmic evolution, including relativistic effects. Current observations suggest the universe will expand forever, accelerating due to dark energy. Eventually, galaxies outside our local group will recede beyond our cosmological horizon. We lose causal contact with them. In this far future, time dilation will play interesting roles. Regions near concentrations of mass will age more slowly than empty regions. Over trillions of years, this differential aging could create observable consequences for how structure evolves. Black holes will be the last massive objects. They'll evaporate through Hawking radiation over unimaginable timescales. The time dilation at their event horizons will be integral to understanding the final era of the universe when even black holes disappear. General relativity is built on assumptions like the equivalence principle and general covariance. Tests that probe these foundations are valuable because they could reveal where the theory breaks down. The equivalence principle says gravitational and inertial mass are identical. This has been tested to extraordinary precision. Any violation would indicate new physics. Satellite experiments like microscope test the equivalence principle more precisely than possible on Earth. General covariance means the laws of physics take the same form in all coordinate systems. This is mathematically elegant, but makes predictions difficult to extract. Tests of general covariance usually focus on observable consequences like time dilation or gravitational waves. Time dilation emerged from Einstein's recognition that space and time are unified into space-time. The constancy of light speed, combined with the equivalence of all inertial reference frames, demands that time must be relative. Different observers experience different durations between events depending on their motion and position. Special relativity describes time dilation from velocity. Moving clocks run slow by the Lorentz factor. This has been confirmed through muon decay, particle lifetimes in accelerators, atomic clock experiments, and countless other tests. Every observation matches theory precisely. General relativity describes time dilation from gravity. Stronger gravitational fields make time run slower. This has been confirmed through gravitational redshift, Pound-Rebka experiments, GPS satellites, pulsar timing, and observations of extreme objects like black holes and neutron stars. Again, every test confirms the theory. These effects are not academic curiosities. GPS navigation relies on relativistic corrections. Particle accelerators require understanding time dilation. Astrophysical observations must account for gravitational redshift. Modern technology depends on relativity being correct. The philosophical implications are profound. Time is not absolute or universal. There is no cosmic now. Different observers can disagree about simultaneity and both be right. The future might exist in some sense already, calling into question free will and the nature of reality. Yet we've figured this out. Through careful experiments, mathematical reasoning, and persistent testing, we've discovered how time really works. The universe is stranger than everyday experience suggests, but it's comprehensible. We can measure these effects, predict them, and use them in practical applications. The experiments we've explored represent over a century of increasingly sophisticated tests. Every measurement confirms Einstein's geometric vision of space-time. General relativity has passed every test, from tabletop experiments with atomic clocks to observations of colliding black holes billions of light-years away. This is one of humanity's great intellectual achievements. We discovered that our intuitions about time are wrong. We developed new mathematics to describe reality correctly. We tested the predictions rigorously. We found them accurate, and we built a technological civilization that depends on this knowledge being correct. The journey from Newton's absolute time to Einstein's relative time changed our understanding of reality fundamentally. Time flows differently for different observers. Gravity isn't a force, but the curvature of space-time. Mass and energy are equivalent. These insights revolutionized physics and enabled technologies that define modern life. Future discoveries await. More precise tests will probe relativity in new regimes. Quantum gravity might reveal corrections at extremely high energies or small scales. But Einstein's framework has stood for over a century of intense scrutiny. The foundation is solid. Time dilation is real, measured, verified, and essential to understanding our universe. Thank you for joining this comprehensive exploration of time dilation. The experiments we've discussed prove beyond any doubt that time is relative, that gravity affects its flow, and that space-time is the stage on which reality plays out. If you found this valuable, please like and subscribe. Every time you use GPS or look at the stars, remember you're witnessing Einstein's universe in action. We began tonight by asking what time is. The answer turns out to be more complex than anyone before Einstein imagined. Time is not a universal background against which events occur. It's woven together with space into a four-dimensional fabric that curves, stretches, and flows at different rates. This understanding emerged from careful reasoning about light and motion. Einstein recognized that if light speed is constant for all observers, and if physical laws work the same in all inertial frames, then time itself must be flexible. What seemed like contradictory assumptions actually require time dilation to maintain consistency. The mathematics followed logically from these principles. The Lorentz transformations describe how space and time coordinates change between reference frames. The metric tensor in general relativity describes space-time curvature. These aren't arbitrary equations. They're inevitable consequences of deeper principles about symmetry and invariance. Testing these predictions required technology that didn't exist when Einstein developed his theories. Atomic clocks accurate to billionths of a second, particle accelerators reaching near light speeds, satellite navigation systems, gravitational wave detectors. Each advance in technology enabled new tests, and every test confirmed the theory. We now have a century of experimental validation. Time dilation isn't speculation. It's established fact, tested more thoroughly than almost any other physics principle. The evidence comes from multiple independent sources using different methods. All point to the same conclusion. Time is relative. This knowledge transforms our worldview. We can no longer think of time as Newton did, flowing equably without relation to anything external. Time depends on motion and gravity. Your experience of time differs from mine if we're moving differently or at different gravitational potentials. Both experiences are equally valid. There's no absolute time to settle disagreements. This raises deep questions. If time is relative, what about free will and determinism? If different observers have different presence, does the future already exist somewhere? These philosophical issues remain unresolved. Physics describes how time works, but doesn't tell us what it ultimately means for consciousness and choice. What's clear is that the universe doesn't conform to our intuitions. Evolution shaped our brains to navigate everyday situations at everyday speeds in weak gravitational fields. We have no intuitive grasp of relativistic effects because they never mattered for survival. But intuition isn't a guide to reality. Careful observation and mathematical reasoning reveal truths that intuition misses. The practical applications of time dilation demonstrate its reality. GPS depends on relativistic corrections. Remove them, and the system fails within minutes. Particle accelerators couldn't function without accounting for time dilation. Gravitational wave astronomy requires understanding curved space-time. Modern technology proves the theory works because the technology works. Looking forward, we'll continue testing relativity with increasing precision. Ultra-precise atomic clocks will probe gravitational time dilation more sensitively. Long baseline interferometry will test relativistic effects across planetary distances. Missions to extreme environments like near the Sun or in Jupiter's strong magnetic field will test the theory in new regimes. We might discover deviations. General relativity might be an approximation valid at accessible energy scales, but breaking down at extremely high energies or small distances where quantum gravity becomes important. Such deviations would be revolutionary, pointing toward new physics beyond Einstein's framework. Or we might continue confirming the theory to higher and higher precision. Each null result strengthens our confidence that general relativity correctly describes gravity and space-time at all scales we can currently probe. Either outcome advances knowledge. The search for quantum gravity attempts to unite general relativity with quantum mechanics. Both theories are extraordinarily successful in their domains. General relativity describes gravity and large-scale structures. Quantum mechanics describes atoms, particles, and fundamental forces except gravity. But they're mathematically incompatible in their current forms. Resolving this incompatibility might require modifying general relativity at very small scales or very high energies. Or it might require changing quantum mechanics, or both. Loop quantum gravity, string theory, and other approaches attempt to bridge the gap. None has yet succeeded definitively. Understanding quantum gravity might reveal what time truly is at the most fundamental level. Does time emerge from something more basic? Is space-time granular at the Planck scale, about 10 to the negative 33 centimeters? Do quantum fluctuations make space-time foam? These questions remain unanswered, but whatever quantum gravity reveals, it will build on Einstein's foundation. General relativity will remain valid as an approximation in the limits we've tested it. Just as Newton's gravity remains useful for everyday calculations even though general relativity is more accurate, the experiments confirming time dilation won't be invalidated. They'll be understood as special cases of a deeper theory. For now, general relativity is our best description of gravity and time. The theory has passed every test. It makes predictions that continue to be verified. It provides the framework for understanding everything from GPS satellites to merging black holes. It works. The experiments we've explored tonight tell a compelling story. From flying atomic clocks around the world to detecting gravitational waves from colliding black holes, from measuring muon lifetimes to observing cosmological redshift, every observation confirms that time dilation is real. The theory predicts, experiments test, observations verify. This is science at its best. Time is stranger than we thought. But we figured it out. We measured it. We tested it. We built technology based on it. And we continue exploring its implications and searching for deeper understanding. That's the legacy of Einstein's insight and the power of the scientific method. The universe doesn't care about our preconceptions. It operates according to mathematical principles we can discover through observation and reasoning. Time dilation seemed impossible before Einstein. Now it's established fact, fundamental to our technological civilization and our understanding of reality. This journey from ignorance to understanding represents human achievement at its finest. We started with intuitions shaped by evolution for different purposes. We recognized those intuitions might be wrong. We developed new mathematics to describe what we observe. We tested predictions rigorously. We accepted results even when counterintuitive. And we built a deeper understanding of how reality works. That's what makes science powerful. It's not about confirming what we already think. It's about discovering what's actually true. Time dilation seemed crazy. But the universe doesn't care what seems crazy to evolved apes on a small planet. The universe operates according to its own principles. Our job is to discover those principles through observation and testing. We've done that for time dilation. The evidence is overwhelming. The theory is secure. The applications are everywhere. This is knowledge we can trust because it's been verified by independent researchers using different methods over decades. It's as solid as scientific knowledge gets. So when you check your phone's GPS location, remember you're using Einstein's relativity. When you look at stars, remember you're seeing light that's been traveling while time itself flowed differently for the photons than for you. When you think about time, remember it's not what Newton thought. It's relative, flexible, and fundamentally woven together with space. This is our universe. Strange, beautiful, mathematical, and ultimately comprehensible despite its strangeness. We've barely scratched the surface of what there is to learn. But what we have learned, including the reality of time dilation, is extraordinary. It tells us reality is far more subtle than everyday experience suggests. And it tells us that we, small as we are, can understand these cosmic truths through observation, reason, and persistence. Thank you for spending this time exploring time dilation with me. Your support through likes and subscriptions helps me create these detailed explorations of physics and astronomy. The universe rewards curiosity with understanding. Keep questioning, keep learning, keep wondering. Time may be relative, but the joy of understanding is universal. Good night, and may your journey through space-time be filled with discovery and wonder.